to our series, Genesis 1, Lessons from Space. The last session we talked about the solar system to lay the groundwork for looking at Earth and how unique it is. So this session we're going to look at Earth, the special nature of Earth. And we're going to see that Earth is very, very different from everything we've looked at so far. And what I want to look at this morning is why. You remember we looked at Mars. It's very barren. There have been 38 years of exploration on Mars. There have been 2 flybys, 8 orbiters, 2 Viking landers back in the 70s, 4 rovers. The rovers have logged a total of 17 years on the surface of the planet and have covered more than 30 miles. And we haven't found a single organism of any type. Not a blade of grass, not a single microbe, not even a fossil of a microbe. So Earth is very different. Genesis says, "Now the earth was formless and empty, darkness was over the surface of the deep, and the Spirit of God was hovering over the waters." You might have wondered, what was the Spirit of God doing when it was hovering over the waters? So we're going to look at that a little bit. We're going to look at the results first, and then we'll look at maybe how this came about or why it is. So in Genesis 1, 6-8, it says, "Let there be an expanse," and God called the expanse sky. And as we have seen, no other planet has a sky like this. Only Venus is the only planet that has clouds, and they're sulfuric acid clouds. So Earth is very different. "Let there be water under the sky, be gathered into one place, and let the dry ground appear." And we saw that the outer planets have no ground to stand on. The other inner planets have no oceans. So again, Earth is different. And God said, "Let the land produce vegetation." And there's so many things that are not remarkable. We see them every day. But in the context of our solar system, it's unbelievable what's on this planet. "And let the birds fly across the expanse of the sky. And let waters teem with living creatures. And let the land produce living creatures." And then he went one step further. And he said, "Let us make man in our image." And he said to the man, "Be fruitful and increase in number and fill the earth and subdue it." And I would submit to you that that's the only command that mankind has ever really taken to heart. So Earth is different. So what is required for Earth to be a haven for life? In other words, what was the Spirit of God doing when it was hovering over the waters? Well, let's look at Earth's environment first. It has a very special environment. If we go back and we look at the Milky Way, and this is a galaxy like the Milky Way, there are places where we simply could not exist. Look at the center, for example. If we blow it up, it's an incredible crush of stars, black holes, other bad stuff. The intensity of the radiation would be unbearable. It would fry us. The gravitational forces could rip us apart. But we're not there in the center. It just so happens that we're 2/3 the way out to the edge of the Milky Way, 30,000 light years. And remember, a light year is 6 million miles, so there are 30,000 of those from the center. And we're not even in one of the arms, which have a lot of things going on in them. There are a lot of clouds and things happening that wouldn't be good for us. We're in between 2 of the arms in a nice, quiet little cul-de-sac out in the suburbs, just exactly where we have to be. And by the way, if we were at the center or in the arms, we wouldn't be able to see the heavens and the glory of God. We've been put on the 50-yard line. So let's look at our sun. It's kind of special. It's compared to the planets, it's huge. You can see it's 109 times the radius of Earth, 431,000 times the mass of Earth, or 743 times the mass of all the planets put together. But look at its radiation. The majority of the emissions from our sun are in the visible spectrum. That's not true for a lot of stars. A lot of stars have the bulk of their radiation coming out in the form of X-rays or gamma rays, so things that are deadly. Our sun puts out mostly visible light, which is essential for life. The visible light is 500,000 times the intensity of the X-ray output. A little unusual. So, and the other thing is, our sun is not a young star, like teenagers, you know, they jump around all over the place. Our star, the sun, is very stable. It's kind of a middle-aged star. It doesn't get excited. It doesn't do anything. And that's very important for us, as you will see in a few moments. It's not like Antares, where if you would put Antares where our sun is, it would engulf the first 4 planets, Mercury, Venus, Earth, and Mars, and the asteroid belt. So there's our sun, the little dot in the circle there, and you can see the orbits of Earth and Mars on the disk of Antares. So it's important to have also the right size star. So the position of Earth with respect to our sun is important as well. Everybody knows that we have solar eclipses. But when you think about what has to happen for a solar eclipse, there have to be very precise positioning of 3 bodies, the sun, the moon, and Earth. So what needs to happen is the sun and the moon need to have the same apparent size. So if something moves further away from you, as you know, it gets smaller. So the sun is 400 times bigger than the moon, but it just so happens it's precisely 400 times further away. And so we see solar eclipses. And because we can see solar eclipses, we know how the sun works. Again, we're kind of on the 50-yard line. Nowhere else in the solar system, and there are well over 100 moons in the solar system, from no other planet could you see a solar eclipse except on Earth. So the position of Earth is more important than that. Around any star, there's a place called the Goldilocks zone. It's the place where a planet is exactly the right distance from the star so that it is possible for it to have liquid water on its surface. And it just so happens that our orbit is right in that favored zone around our sun. We saw earlier when we in the previous session that those planets that are inside of us are very hot. And those that are beyond the orbit of Earth, beginning with Mars, are really cold, too cold to have liquid water. Earth is in exactly the right spot. And more amazing than that, if we look at this, Earth is right on the inner part of this zone, which is shown in gray here. Earth's orbit is the gold ring, and it's 5% from the inside of that. So what that means is if the sun brightened by just 10%, we would be inside of that zone. It would push the zone out beyond us, and we would be too hot. And if it stayed brighter, all our oceans would eventually evaporate, and this would become a dry, dead planet, just like Venus. So it's very important, as I mentioned before, that our sun is stable, very stable, because our existence depends on its stability. Let's look at some of the shields we have from the deadly aspects of space. Everybody recognizes that, I guess. It's probably the most expensive footprint in human history. So here's an astronaut on the moon. He's alive because he has a suit and a backpack, all that weighs about 300 pounds, and it provides him with not only with oxygen, but with thermal control. You see on the side that's facing the sun, he's scalding hot, and on the other side, he's very cold. So you have to have an air conditioning system that equilibrates all this and keeps him in the right temperature zone. So it's a very harsh environment. But the moon orbits Earth, doesn't it? So the moon is in that special zone of the sun where it's possible to have water on the surface. But there's no water here. There's no atmosphere here. It's a harsh environment. Why is that? Why isn't it like Earth? It's the same distance from the sun. Well, it turns out that size matters. The moon is not big enough, doesn't have enough gravity to hold volatiles to its surface. So if it ever had water or an atmosphere, they simply evaporated into space and were lost. And the result of that is traumatic. Look at the surface. You see, the moon has no protection from meteors. And I'll just look at this for a second. Here's a meteor we'll look at in some a meteor crater from a meteor we'll look in some detail. And you see the peak in the middle. We saw that on Mars. As we zoom into the peak, you can see that this looks like a giant ash heap. Not very pretty, not very interesting, nothing like the views we saw of Earth. So the moon is too small. Size is important. Jupiter is so huge and has such huge gravity, it would probably crush us. We couldn't live in that. The Earth is just right. So the Earth, because it has enough gravity, holds its atmosphere to its surface. That's another shield. You can see our atmosphere up to a height of about 60 miles. That's called the limb. It has a density of 15 pounds per square inch. The impact velocity of meteors coming onto Earth is in excess of 25,000 miles per hour. So our atmosphere intercepts them, so to speak, and slows them down. Is that important? Well, big meteors are very rare. A fairly big one went over Russia a couple of years ago and knocked out windows and scared everybody to death, but they're very, very rare. But smaller meteors are more, the population of meteors starts with very few that are big, but goes up exponentially as you get smaller. So when you get down here to grain-sized meteors, grain-sized meteors, there's a virtual drizzle of meteors continually. 10,000 metric tons of dust fall on the Earth every day, the result of burned up meteors. And meteors are composed mostly of water ice. So that's just the dust that's on the ice. A lot of meteors come down on the Earth. Well, how important is that? Well, at 25,000 miles per hour, a meteor the size of mass of 3 grains of rice would have the destructive capability of a 140 grain bullet fired out of a .30-06 rifle. So if the atmosphere weren't there and you stepped outside, you would be riddled with .30-06 rifle bullet equivalent of meteors. So we have to have an atmosphere to be here. But there are other reasons we need an atmosphere. You see, the sun is the mother of all nuclear reactors around us. It emits all kinds of bad stuff, cosmic rays, million EV and billion EV particles, very energetic particles that'll simply penetrate you and burn a path through you. Infrared, ultraviolet, which causes cancer, X-rays, gamma rays, all kinds of electromagnetic radiation and particulate radiation. Everything that a nuclear bomb puts out, our sun puts out. So how is it that we're here? We don't have time to go into all of them, but let's look at one case. We all know that the Earth has a magnetic field. I'm sure you've all used a compass. But what you might not realize is that magnetic field is much more important than helping us find our way around the Earth. this is a schematic of what happens. You have the Earth, and it has a dipole field, kind of like a bar magnet. And you have radiation coming from the sun, particles, very energetic particles that are charged electrically that would kill you. But a charged particle cannot cross a magnetic field line. That's just one, you have to trust me, that's one of the things we found in physics. But they can slide along the field line, kind of like beads on a string. So the particles are pushed away and diverted by the Earth's magnetic field. In return, the field suffers compression. So you see that it's crunched in on the sun side and pulled out on the back side. If you look at what this actually looks like, it's more complicated than that, but this is the same thing. You have the Earth here in the center. You see the Van Allen radiation belts right around the Earth. And then you have the effect of the Earth's magnetic field. This is called the Earth's magnetosphere because it's a bubble around the Earth that's created by the Earth's magnetic field. And as the radiation comes from the sun from the left, the charged particles are diverted and they spiral around the field lines and go down, and they can reach the Earth in only two places called the polar cusp. There's one at the North Pole and one at the South Pole. And that's where the field lines come back in to the poles of the magnet. So at these points, you have these super energetic charged particles screaming down into the atmosphere, exciting the atmospheric molecules and atoms and causing them to fluoresce, and they emit light. And this is a picture of it taken from the space shuttle. And you can see these streamers coming down where these energetic particles are coming down into the neutral atmosphere. Of course, from below, we recognize this as the aurora borealis, or australis is the one we actually saw. So we have a very effective radiation shield. Everybody's aware of the ozone layer. There was a lot of concern about the ozone layer going away. Why is that important? Well, because ozone is a ultraviolet shield. You see, ozone gas is oxygen, but instead of having 2 atoms per molecule, like the oxygen we breathe, it has 3. 3 atoms of oxygen make ozone. And it has very different chemical properties than O2. O2 is necessary. We couldn't live without it. But O3 is poisonous. But the good thing is it's a very, very effective ultraviolet absorber. So the ultraviolet comes in, and when it reaches this layer, it's absorbed and re-emitted in a different benign form. So here's a little more detail of what happens. You have altitude on the left y-axis, and the ozone density or flux density on the x-axis. And the curve there, the little peak that goes out to the right, that's the density of ozone as a function of altitude. The ribbons coming down represent the intensity of ultraviolet radiation. And there are 3 bands, ultraviolet A, B, and C. A being the least energetic, C being the most. So ultraviolet A gives you a suntan. That's about it. And you see that roughly half of that is screened out. Half of it reaches the surface. Ultraviolet B will cause cancer. It's dangerous. And almost all of ultraviolet B is screened out. Just a little bit comes through, and that's why your better sunglasses have ultraviolet B screening. Ultraviolet C is deadly, and all of C is screened out. So I would submit to you that if you're an engineer and you were assigned the task of designing a UV shield for our planet to screen out UV, you could not design a more efficient way of doing it than this. So the Earth has a special temperature as well. We saw that Mercury and Venus are extremely hot, and Mars on out are way too cold. So what is it that helps us be able to have the right temperature? Well, it's a number of factors, actually. It's, first of all, where the Earth is in its orbit. It's in that zone where it's possible for a planet to have liquid water. But there are other things involved. The amount of cloud cover, for example. The atmospheric composition. Everybody's worried about too much carbon dioxide. Atmospheric circulation, the ocean circulation, the tilt of the axis, and radioactive decay in the Earth's core. All of these contribute to the thermal balance of the Earth. So let's look in a little more detail. The Earth's atmosphere is mostly nitrogen, 78%, 21% oxygen, and 3% carbon dioxide. I'm sorry, 0.03% carbon dioxide. There's a lot to do about nothing here. It's more than that over cities, of course, but the global warming is global, right? Global warming. The global concentration is 0.03% of the atmospheric density. Not enough to cause, anywhere near enough to cause global warming. And you have water vapor and cloud cover. All of these things contribute to the thermal balance. There's an interesting thing happened in the first Gemini, the first Apollo 1, which burned on the pad. At that time, the crew cabin had pure oxygen at an increased pressure, above atmospheric pressure, because that helped the astronauts get through the physiological challenges of the launch and the accelerations they go through. And they had combustible materials in the cabin. So when the fire broke out, I don't know if you ever did this, but when I was in high school, we made some oxygen and had a beaker full of oxygen, a test tube, and we struck a match and lit a splinter and blew it out, and it's no fire, but it's still hot. And you put it down into the test tube and poof, it just explodes. That's what happened in the cabin. So NASA learned an important lesson. Nitrogen is there for a reason. It's no accident that our atmosphere is 78% nitrogen. You see, nitrogen is an inert gas. It doesn't do anything. It just gets in the way of the oxygen. So think of a dance, and you got these teenagers bebopping around, and you got some old people who don't dance, who are just out there. And the more old people there are, the more trouble the teenagers are going to have dancing. So we have just the right mixture. It's possible to have fires, but they don't explode out of control. If we had a pure oxygen environment on Earth, every pile of leaves would burst into flame. Everything would burn that could burn, and eventually there would be no life on Earth. So the mixture is important. I want to look at the uniqueness of water. You know, and you all know this, the thing is when water freezes, the ice floats. If you've ever drunk iced tea, you know that. But it's a lot more important than that, if you've thought about it. Because ice floats, when the sea freezes, you have sea ice, and it floats on the surface of the ocean. And so when the sun comes back up the next summer, because the Earth's axis is tilted, this area gets more sunlight. And the ice on the surface of the ocean melts a little bit, breaks up, icebergs break off, and they float down to temperate zones where they melt. This keeps the ice caps of Earth from getting too large. They're regulated by this. So what if ice didn't float? Every winter, you'd have sea ice, and it would sink to the bottom of the ocean. Now, water, as it gets colder, gets more dense and more dense. And the colder it gets, the denser it gets. So cold water sinks until it gets to 4 degrees centigrade, where it begins to expand. And by the time it becomes a solid, it's expanded 10%. So ice actually, when it's floating, 10% is above the water and 90% is below the water line. So icebergs are a lot bigger than they appear. But if they sunk, they would be in the coldest water in the ocean, just barely above freezing. They would be perpetually shielded from the sun, and there they would remain, these icebergs, ice. And every winter, the same thing would happen. More ice would sink, until finally you have solid ice oceans. Maybe a few puddles on the surface during this summertime, but not enough to support life, become a frozen planet. So the fact that ice floats is critical for us, not just for keeping the ice out of the bottom of your tea glass. Let me introduce you to Matthew Fontaine Maury. He was a naval officer in the United States Navy back in the 1800s. He was ill one time and was bedridden, and his grandson, the story goes, was reading to him out of the Bible, and he was reading out of Psalms 8, chapter 8. And the birds of the air, verse 8 says, the birds of the air and the fish of the seas, all that swim in the paths of the seas. And Matthew Fontaine Maury asked his grandson to read that again. And then reportedly he says, if God says there are paths in the seas, they're there and I'm going to find them. Nobody had any idea what this was. In fact, at this time, the main trade partner with the United States was Britain. And ships would come from Britain, sailing ships, and they would, out in the Atlantic, they would run into this invisible wall. And they would sail for days and days, and finally they would break through and they would come on over. It was a real economic problem. They would be, waste a week or something out there. Well, here's what Matthew Fontaine Maury found. The ocean currents. The most well-known to us probably is the Gulf Stream. It takes warm water out of the Gulf of Mexico and flows northeast across the Atlantic Ocean. That's what they ran into, the Gulf Stream, and goes up by England and ends up somewhere around Sweden. I was in Sweden a few years ago, and it was colder in Huntsville, Alabama than it was in Stockholm, Sweden, because of the Gulf Stream. You may not realize this, but England is on the same latitude as Maine. And it rarely snows in England because of the Gulf Stream. But it was a problem for the mariners. But it's only about 60 miles wide. So once it was discovered by Matthew Fontaine Maury, they realized that instead of fighting it, they could simply sail across it in no time, and it cut off tremendous amount of time they used, saved literally millions of dollars back then. And Congress decided it was such a great discovery and had such great economic value that they would award Matthew Fontaine Maury with a cash award. But then they came back to their senses and gave themselves a raise instead. So here's a man that became famous and achieved a lot. I'm always skeptical about these kind of stories. So a number of years ago, Margaret and I were up in Annapolis for a wedding, and we went over to check on this story. And it turns out that the engineering building at the Naval Academy has a plaque that says Matthew Fontaine Maury, the father of modern navigation, and talks about what he did. This man achieved this simply because he took God at his word. If the Bible is the inspiration of the Almighty, even though its purpose is the salvation of mankind, not to tell us how the universe works and how it was created, but if the Creator is the inspiration for the Bible, then there should be places where in just discussing things are going to shine through. And this seems to be one of those places where just a little bit you see the way God created things. In Genesis 1:2-10, he says, and the Spirit of God was hovering over the waters, and God said, let there be light, and there was light. And God saw the light and said it was good, and he separated the light from darkness. And he called the light day and the darkness night. And there was evening and there was morning the first day. And God said, let there be expanse between the waters and to separate the water from water. And so God made the expanse and separated the water under the expanse from the water above it. And it was so. And God called the expanse sky. And there was evening and there was morning the second day. And God said, let the water under the sky be gathered together in one place, and let the dry ground appear. And it was so. And God called the dry ground land, and the gathered waters he called seas. And God saw that it was good. You know, Werner von Braun was very impressed with nature. And he says, one cannot be exposed to the law and order of the universe without concluding that there must be a divine intent behind it all. And there are things we don't have time to go into, but the probabilities of us being here accidentally are so minuscule, they become an argument for the existence of God. The most striking result of almost 60 years of space exploration is the unavoidable realization that the Earth is very special, possibly unique. And in a real sense, the Earth is an oasis, a garden in which God has planted life. And you think about it, this planet is absolutely nothing like anything else we know about. Did it happen by accident? The probabilities say it didn't. So we'll come back and we'll talk about the implications of everything we've seen so far.